After many years of teaching this, I can tell what you're going to do wrong on a midterm. What you're going to do wrong in magnetic circuits is that you're going to mix up the mean path length, which is L, and the cross-sectional area, which is A. Because when you look at the shapes, your mind kind of tricks you. So let's say, for example, this is a toroid shape. Now, this could be a toroid that has a rectangular cross-section, and that would look something like this. Here's a rectangular cross-section, looks something like this. And then this could be a toroid. Toroid basically means donut shape, which has a round cross-section, which 3D kind of looks like this. It's a donut. Or let's say we have a bar. And we're going to wrap some coils. We're going to wrap coils around this bar. Then that's a different shape. So here's a bar. And that bar can have a rectangular cross-section, or it can have a square cross-section. I suppose it could be a circular cross-sectional bar as well. So there's difference between the mean path length and the cross-sectional area in these examples that I'm showing here. And the mean path length, we have to really think about the English language of what it means. This is mean path length.
Is average?
Mean means average, yeah. Average path length. And then we have to think the path of what? It's the path that the magnetic flux is traveling on. So we have flux that is being induced in these shapes when we put a coil on them. So let me put a coil on each of these shapes. Let's say the coil goes around here on this one. All right, a coil goes like this, wrapped around this one, same as this one. The coil goes like this. There's current in the coil. But the flux lines are what you have to have a path of. It's a path of the flux lines. Let's see, this is a coil is wrapped like this. All right. Now we have to know where the flux lines travel. And in this case of a toroid, the flux lines travel around the toroid. They travel like this. And they, some of those flux lines are small if they're on the inside. Some of them are traveling a long path if they're on the outside, but those are your magnetic flux lines. They have a direction, and all of the 5 principles of magnetism apply to them. Now, that's how it would be in a toroid. It would be like that in this toroid as well. Some of those flux lines are going to be traveling a really long path on the outside. Some of them are going to be traveling a path length that is not as long on the inside. But the average or the mean path length, the mean of those will be in the middle. So the mean path length will be in the middle of those because L means mean path of all of the flux, average path of all of the flux. Now, when you look at the bar magnet, some of them travel this length. Some of them travel, it's the mean path of flux inside the material, and that's the tricky part as well. It's inside the material. In material. It's inside the material. So when you look at the flux lines of a bar magnet, they come out like this, right? Or an electromagnet that you made. But their mean path inside the material is simply from one side to the other. That's their path. That's the path of this one. That's the path of the middle one. That's the path of another one. That's the path of another one. These are traveling same length. Same mean path length inside the material, aren't they? These ones had different. These ones had long length or short. We want the middle. All right, so that is the mean path length. And let me show you what you would actually use then of the mean path length. For this one, for this first toroid, that is a rectangular cross-section toroid, I would say I have an outer diameter. I have an outer diameter. I have an inner diameter, but the mean path is the middle. That's the path length I would use for L. And then on this one that is a donut shape or a circular cross section, I would say, oh, we have some long paths, we have some short paths, but it is a mean path that I want. The mean path. And then for this one, I'll say they all went the same path. So the path length is that of the length of this magnet. That's how you do mean path length. And now cross-sectional area is something that people do wrong. Cross-sectional area I'll do in pink here. Cross-sectional area, people look at this donut and they say, great, I'm going to take this as my area because I like looking down on a donut and saying that's the surface area of the donut. But that's a surface area. That is not a cross-sectional area. So please do not calculate pi r squared using the radius of the donut. Similar to this one, the cross-sectional area, it's a cross-sectional. It is a plane. It's area planar, if that's how you like to think about it. It's a planar area. It's not, let's look down on this, and you've given me two diameters, inner and outer, so therefore I'm going to use that for my cross-sectional area. No. You use that because you needed it for your mean path length. You needed outer diameter and inner diameter. For your cross-sectional area, please do not use that. It is not the cross-section. It's sort of a bird's eye view there. Cross-sectional area, which is denoted by a pi symbol, cross-section, means that you take a section. Let's draw a section maybe in, I need a new color, maybe in red. So I'm going to cut a section through here. This is a plane. I'm going to cut a planar section through. That's where the word pi comes from. Pi means plane. This is a plane. Okay, it's like a piece of paper. It's a plain pi. It's like a piece of paper. Here's another one. I took it and I cut it through there. And when I cut it through there, what shape does it cut through on is what I'm going to be looking at. Well, the shape that cuts into it, in this case is a rectangle. And that is my cross-sectional area. That's my cross-sectional area, A pi. Okay? Now, in the case of this toroid that is sort of donut shape, I'm also going to cut a plane. I'm not going to look down on my donut on my plate. I'm going to say, oh, I cut this donut in some pieces for my friend. And when I cut this donut into pieces for my friend, my knife goes through a section that looks like a circle. It looks like a circle, doesn't it? When I cut through it like a cake, like a bundt cake or a donut. It's like this. So that is A pi. Cross-sectional area to do your magnetics calculations. That is A pi. Got nothing to do, well, it's got a little bit to do with the inner and outer diameter, but it's a cross-sectional area. When I cut the plane for this bar magnet here, I'm going to cut the plane like this. It's a cross-section like this. And now you're thinking, well, how do I know that that's the cross-section? And I'll show you why. I'll show you why. I'll show you which cross-section to cut. This one happens to be rectangular, so the plane's going to look like this. And that's going to be your cross-sectional area for your calculations like reluctance. All right. L is going to be the mean path length for your reluctance equation. A is going to be your cross-sectional area for your reluctance equation. And that is the mistake that most people make in magnetic circuits when they first learn. Now, why did I cut this cross-sectional area here? Because I'll put a definition of it here. A pi, or a cross-sectional area, is that which has flux lines cutting through perpendicularly. And what that would look like to us if we're looking, if from our definition of flux density, the flux lines went through it like piercing an arrow. The flux lines went through this, they went in one side and out the other. Look at the flux density. They went through this like this. So the cross-sectional area is the one that received, it received all of those piercings of flux moving through them. That's the cross-sectional area. They received, it's the area that received perpendicularly the flux moving through all of these. All right, so I encourage you to really think about the difference between mean path length and cross-sectional area when you're calculating the permeability and reluctance in magnetic circuits problems. It is absolutely the most duplicated error in calculation, and I hope that's helpful.